Hi, my name is Paul Medvedev. I'm a professor at Penn State University. Today I'll be presenting a paper published in ISMB Proceedings. The title of the paper is The Minimizer Jaccard Estimator is Biased and Inconsistent. This is joint work with Mahdi Belbasi, Antonio Blanca, Robert Harris, and David Koslicki. Sketching is a widely used technique to handle the ever-growing data sizes in bioinformatics. A sketch basically is just a much smaller representation of a data set. If you have a sketch, it can allow downstream algorithms to be faster and to use less memory. Or if you'd rather view those as fixed resources, it allows downstream algorithms to tackle much larger data sets. There are several examples here that I list of sketching techniques in bioinformatics, and also several examples of downstream applications that rely on sketching. However, one must beware when using sketching in that sketch can create inaccuracies relative to the original data set. And that's what I want to talk about today. Arguably the most popular sketch in bioinformatics is the minimizer sketch. It's best illustrated with an example. Here I have a sequence ACG-GAT, and I'm going to split it up into its constituent k-mers for k equals 2. So I've got AC, CG, GG, GA, and AT. These are the k-mers in my sequence A. Now I have a hash function which I use to hash each one of these k-mers to a number between 0 and 1. Okay. Next, I take a window of W consecutive k-mers. Here W equals 2, but in practice you might think of W as being more like 20. And in this window we find the smallest hash value. When the k-mer that has the smallest hash value is going to be called the minimizer of that window. And we add this minimizer to our sketch. We then shift the window, compute the new minimizer, and add it to our sketch. Now sometimes, in fact often, the minimizer doesn't change. It's already in our sketch. So then we don't do anything and we go on. So here the original sequence has been sketched, and the sketch is the three k-mers CG, GG, and AT. Now the idea of this sketch is that on one hand, when you shift a window, you are unlikely to change the minimizer. Okay. So you create this kind of the sparse selection of k-mers. On the other hand, you are guaranteed that for any window of W k-mers, at least one of those k-mers is a minimizer. So this sketch has this nice property that even though it's sparse, it's well spaced out, and there's this local guarantee. Okay. So minimizer sketch is used all over the place, including sequence alignment, mapping, assembly, error correction. What we want to focus on, though, is where it's used to estimate the Jaccard similarity. The Jaccard similarity, informally, is just the percent of k-mers that are shared between two strings. More formally, let's look at this example. I have sequence A and a sequence B. And in this matching graph, I put an edge between any two k-mers that are identical. So if we let S be the number of shared k-mers, in this case 3, and we let U be the union of all the size of the union of all the k-mers, the number of k-mers that appear in at least one of the sequences, here that's 7, because you have 10 total, but 3 of them are duplicates. So the Jaccard is then 3 divided by 7, the shared over the union. That's the Jaccard similarity. Now, the Jaccard similarity is actually computationally difficult to compute because it involves doing an intersection of this possibly huge k-mer data sets. In fact, it's rarely computed. One of the things that makes it so nice is it's amenable to using sketching. And in fact, we can use the minimizer sketch to estimate the Jaccard. And it's very simple. We just take the Jaccard similarity between the sketches themselves. And we use that as an estimator for the Jaccard similarity between the full sets of k-mers. We call this the minimizer Jaccard estimator, J hat, sometimes called the winnowed Jaccard estimator. So in this example, we can look at just the red guys are the sketches, and there's only one edge connecting two red guys. So number of shared there is 1, and the number of red guys in the union, well, you have 5, one of them is shared. So that's 4 union k-mers. So this J hat estimator is 1/4. This minimizer Jaccard estimator is used in a popular read mapping application called mashmap. The main question of our work now is the following: is J hat an accurate estimator of the Jaccard? Now, the Jaccard estimator is a random variable because it depends on this random hash function that generates the sketch. So every time you will get a different value for the estimator. Therefore, we can't possibly expect it to always be correct. Then how do we think about accuracy in this case? Well, turns out statisticians have a really elegant way to do that. We want our estimator to have the following property. Even if at any point the estimator will give you a wrong value, you want that on average it gives you the correct value. More formally, that the expected value of the estimator is equal to the true value. This type of estimator is said to be unbiased. Now, sometimes this is too strong of a property. You might have that when the sketch size is small, the estimator has a bias. But a slightly weaker property would be that as you increase the size of the sketch, you get rid of the bias. And the estimator that has this property is said to be consistent. Now, these properties are really important for an estimator because you can imagine a downstream application that can sort of tolerate uncertainty in the estimator, but it doesn't want its results to tilt one way or the other, right? Whatever it's trying to predict, it doesn't want it to be biased. And in fact, a very popular Jaccard estimator has this property of being unbiased. This is the min-hash Jaccard estimator, and it works just like the minimizer Jaccard estimator, except it's using a different sketch. It's using the min-hash sketch instead of the minimizer sketch. Now, the two sketches are somewhat similar, at least in spirit, and so one would imagine that the minimizer Jaccard estimator is also unbiased. So to dig into this, we looked at mashmap, this sequence mapper which relies on the minimizer Jaccard estimator. And we found that when we look at reads mapped to their true location, that the divergence that mashmap reports, even averaged over many, many replicates, is significantly higher than the true divergence across different values of divergence. So this indicates a bias in the output of mashmap. And then we wondered if this is being caused by a bias in the estimator. So why should the minimizer Jaccard estimator be biased? Well, one of the intuition, but not the whole picture, is that the Jaccard similarity does not depend on the order of k-mers. It's just an intersection between sets. However, the estimator does depend and is sensitive on the order of k-mers. And that is because whether a k-mer makes it into a sketch or not depends on the k-mers that are in its nearby window. Okay, so how the k-mers are laid out along the whole sequence all of a sudden makes a difference. I can make this example very concrete. So here we've got two sequences that share the same k-mers, but they're permuted in the sequences. So they appear in different order. The Jaccard in this case is 1 because the set of k-mers is the same in A and in B. However, the sketches of the top and the bottom sequences are possibly going to be different because, as I mentioned, the ordering is different and the windows surrounding each k-mer is different. Okay? So if the sketches are sometimes different, that means the estimator will sometimes be less than 1. And even if it's sometimes still 1 and sometimes less than 1, that means that in expectation it has to be strictly less than 1, creating a bias because the Jaccard is always 1. However, this doesn't really explain everything, because what we'll find is that even in a situation like this, when the order of the shared k-mers does not change, we still have a bias. So for this intuition, I would ask the opposite question. Well, why should the estimator be unbiased? It's true, there was some intuition about how it's similar to the min-hash estimator, but that's just kind of a hand-wavy feeling. What about some concrete intuition for why this should be unbiased? Well, the way I thought about it is that as you have a higher Jaccard similarity, it means you have more shared k-mers. And if you have more shared k-mers, you have more shared minimizers, at least probabilistically. And if you have more shared minimizers, you have a higher estimate value. So in this way, both the true value and the estimate value will increase as the number of shared k-mers increases between sequences. But the problem with this intuition is that lots of functions exist that have this property. So here I'm plotting the Jaccard for a sequence, two sequences of length 100 as you vary the number of shared k-mers. And the y-axis here is 0 to 1, and the Jaccard is a function that looks like this. Now you could also have functions that look like this or like this. Both of them have the property that they increase as the number of shared k-mers increases. But each of these would actually be a biased estimator, right? Because like if you fix the number of shared k-mers, the value of the true Jaccard is different than the one the estimator would give you. Now you might ask, well, but these aren't just some functions out of thin air. They actually have a very similar structure. They're this ratio. And that's true, except the number of shared minimizers is not necessarily proportional to the number of shared k-mers. And this is what we'll find. Okay. So basically the intuition of why j hat should be unbiased sort of breaks down when we think about all these other functions that could also share this property with with the true Jaccard. Now I'm ready to present the theoretical results. First, we make a key observation. It is enough to consider the simpler case when A and B are duplicate free. In other words, A and B may share k-mers, but within each sequence, each k-mer appears just once. And the reason we can focus on this case is that if we prove that even for this more restricted family we have bias, it immediately implies that there's bias for the more general family. In other words, since we have a negative result, it actually suffices to prove it for a subset of the general family. Now we're going to have 4 theorems. The first theorem states that the absolute value of the bias here is given by this term b plus an error term epsilon. The important thing about epsilon is that it goes to 0 as the sequence gets long. Now b, we have an exact derivation of what it is. It's just a function of the matching graph, but it requires a lot of hairy notation, so I can't even write it down here for you. Suffice it to say that if you have the matching graph, you can compute b. Basically, this theorem gives us a formula for the bias up to this small error. Now, theorem 2 says that this b is actually, except for corner cases, it's strictly negative. So in particular, if the Jaccard is strictly between 0 and 1, then B is strictly negative. This shows then the minimizer Jaccard estimator is biased. And the bias can be derived from the matching graph. Now you might think, well, if you can do that, why don't you just add B to your estimator, and that will give you an unbiased, or at least a consistent estimator. Well, if we do that, it defeats the whole purpose of the sketch, because to compute the term B, we need the matching graph, and that's not something we can get from the sketch. So we need to go back to the original sequences, which really defeats the point of having the sketch. Then we wanted to look at more concrete families of sequence pairs. So the first are what I'm calling sparsely matched sequences. That is, the windows between any two shared k-mers never overlap. So the edges are spaced apart from each other. This is supposed to informally capture the idea of unrelated sequences, where these edges are probably happening by chance. In this case, we can derive a nice formula for B that actually simplifies to be a function of W rather than the whole matching graph. And then once we plug in the numbers, we see that the expected value of the minimizer of the estimator is at most 63% of the true Jaccard. So that's quite a large bias. It tells us that if Jaccard is 10%, then the estimator is not going to give us more than 6.3% on average. On the other end of the spectrum, we wanted to capture two sequences that are related to each other. So here we have sequence A on top and sequence B, the bottom one, generated by mutating every jth nucleotide for some j that's larger than the window size. Now remember, a mutation of a nucleotide destroys k k-mers. So here k equals 2. We've got these blocks of unmatched k-mers, whereas they're separated by these blocks of matched k-mers. Here we can again get a formula for B. It's a little bit more hairy, but it's just a simple formula that one can plug in the numbers and compute. So for some like reasonable numbers, you'll get that the expected value of the estimator is about 10% smaller than the true Jaccard. So next, we looked at the extent of empirical bias on real sequences. In this plot, I'm showing the true Jaccard compared to the estimated Jaccard averaged over many replicates. For unrelated sequence pairs, you see that the bias can be quite huge. For a Jaccard of 0.9, for example, the estimator only gives 0.4. For related sequences like this, the estimator is biased but smaller. And this intuitively lines up with our theoretical results. We also looked at the effect of bias on the mashmap divergence estimates that we saw before. We found two reasons for the bias in the divergence. One was, in fact, the mashmap, the estimator bias. The other is an error in the formula that mashmap uses for divergence. Once we corrected for both of these, the divergence estimates were exactly correct. In some cases, the bias of the estimator accounted for the whole bias of the mashmap divergence. To summarize, we showed that the minimizer Jaccard estimator suffers from bias and inconsistency. On unrelated sequence, the bias can be drastic, while on related sequences, the bias is smaller but still substantial. We observed that the bias cannot be removed by changing the window size, and that this bias causes inaccurate estimates of identity during mapping. So where does that leave us with this estimator? Well, it's not necessarily ruling out the possibility of using it. Just make sure that you empirically test the bias for your application before using it. And make sure that the bias is acceptable in your application. So in this case, if you're doing read mapping, then probably 1.5 versus 1% divergence is fine. But if you're doing fine-grained phylogeny reconstruction, then probably that's not an acceptable error. Or you can just switch to using a sketch that's consistent, such as the recent fragment hash, mod hash, or universal minimizers. Thank you for your time.